So with probability, the actual arithmetic is super simple. Where you're going to get bogged down with, like anything else, is kind of with the vocabulary. But first thing we need to do is talk about the different type scenarios. So you're going to be talking about simple probability experiments, like, hey, if I roll a die, what's the probability of getting a 2? Something like that. So today we're really, really basic, and we're going to step it up pretty quick over the next few days. But today's going to be pretty simple. Okay. All right. So an event is just something that happens. Okay. So rolling the die would be an event. The total sample space would be all the possibilities. So if I roll a die, how many sides does a die have? 6. So it would be 1, 2, 3, 4, 5, and 6 would be my sample space. The event is any specific one. If I flip a coin, I can get heads or tails. So the total sample space would be H or T. So we're going to abbreviate a lot. So anytime I do an abbreviation, if you're not sure, just let me know and I will explain it. But hopefully heads and tails, H and T, are pretty simple. You're going to have some pretty graphics that we're not going to use because they're from smartboards. All right. So an experiment is the process of actually measuring. So you have what's called theoretical probability and experimental. We'll talk more about this in a little bit. But experimental is where you actually roll. So if I, or in this case, flip a coin. If I flip a coin 1,000 times, how many times should it show up tails? 500. But in actuality, when you flip a coin, it's probably not going to be 500. It'll probably be a little bit more or a little bit less. So theoretically, it should go 500. Experimentally would be actually flipping the coin 1,000 times. We will not be flipping a coin 1,000 times. If we do it, we will use a simulator. In other words, we'll just let the computer flip the coin for us and tell us how many times it showed up heads and tails. Because you have things called random number generators. And if you've done any coding at all, you might have had to use them from time to time. And if you haven't, that's okay too. I'm not going to make you code the random number generator. The computer will do it for us. All right. So if I flip I got 2 possibilities, flip a coin. But if I flip it twice, now I have 4 possibilities. I can have heads and heads and heads and tails and tails and heads and tails and tails. So the probability of me flipping the heads twice is 1 out of the total of 4 possibilities. That's all. Okay, 25%. How about if I flip it 3 times? What's the possibility of getting 3 heads? 9. 9?
36.
It's a half times a half times a half. And a half times a half times a half is 1/8. Okay, so the more times I flip, the less likely it is I get the same result every single time. All right. Here is our first example. Suppose a box contains 3 balls, 1 red, 1 blue, 1 white. 1 ball is selected. Its color is observed. I have a red ball. And then they put it back. And the balls are scrambled again. The ball is selected, and the color is observed again. What's the sample space of the experiment? And this is what you're looking at. Okay. So this is a prettier version. Mostly what we're going to do is make a tree diagram. So I'll show you an example of that right now. Okay. So easiest way to make a tree diagram, I'm going to use the same thing. I'm going to ignore the box part. I'm going to put R for red. Tab, 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 tab. B for blue. Tab, 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 tab. W for white. And then I'm going to use our lovely tools. You can use the drawing tools, or in this case, I'm going to use my shape tool. And I'm going to use the line tool. Since I have 3 possibilities, I'm going to make 3 lines coming out of R. So 1, 2, 3. And I'm not going to be too picky. I'm not checking to see angle measures or anything like that. So I still have 3 possibilities. So I'm going to make another text box down here. So I can have red. I'm basically reproducing what they have there. It's not going to look as pretty because I don't expect you to make like rounded rectangles and stuff, but you should be able to make text boxes and connect things. Okay. B. Oh, let's make one last. Caps lock. Space, 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 space. W. And then we repeat it again. We can have red. I can have blue. I can have white. And you want to be consistent. I mean, you don't have to do it in order like this way. But if you go back and look later, you might be a little confused. Okay. So in total, I have, here would be how I would write it. Okay. So if I make a new text box, and these are all my possibilities. So this would be my sample space in a slightly different way. Oopsies. A caps lock deal. Don't capitalize it for a sample. Oh, I keep having caps lock here. Sample space. So I could pick a red. Now I'm going to put it back on. And a red. Or red and a blue. A red and a white. So that's all. That's exhausting all my possibilities of red. And then I could pick a blue and a red. 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 There we go. And then a blue and a blue and a blue and a white. I have one more chance. I could start with a white and then pick a red and a white and a blue and a white and a white. This time, Ahmad, how many choices do I got? What did you say last time, Ahmad? 9. There you go. Okay. Because I have red, 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 blue, red, white, blue, right, blah, 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 blah. I've got a total of 9 different possibilities when I pick them 2 at a time. Okay. I'm actually not picking 2 at a time. I'm picking one, putting it back in, and picking a second one. So this would be my entire sample space. So when I set up my probabilities, my denominator would represent the total number of items in my sample space. In this case, 9. Okay. So take that into account when we answer the next questions. So probability, capital P, A, we just usually use a capital letter to represent whatever event it is. In this case, it will be the probability I choose a red ball and then a white ball. So I go back up here. How many times do you see R and then W? Once. So it's 1 out of 9. That's it. That's the probability. Okay, so 1/9. Hey, what do you think we're going to be dealing with lots of with probability? It's almost exclusively fractions. We will delve into decimals a tad, but mostly fractions. Probability of a blue and then either red or blue. So now instead of 1, it's 2. That's all you got to do. It's not any more complicated than that. Okay, questions so far? Basic stuff, right? Okay. So before we do the next one, I'm going to use this white space up here. We are going to talk about a standard deck of cards. I found out a few years ago that most of y'all don't play cards anymore. Or if you do, you have no idea what a standard deck of cards really entails. Like, you know there's aces and jacks and queens, but you don't know how many of each. So we're going to make sure everybody understands. I have 4 suits in my hand. So we're going to write them down so you are clear as to what the 4 suits are. So we're going to make a little text box right here. Standard deck of cards. What are we not going to include? No jokers. Okay. So standard deck of cards. So it is understood. No jokers. So if you want to put that down, go ahead. All right. We have 4 suits. They are clubs, which are black. And if I really am insulting your intelligence, I apologize. Okay. We have diamonds, which are red. We have spades, which are also black. And we have, what's left? Hearts, okay, which are red. Okay. So just to show you, the spade, okay, the club looks like a little clover, heart looks like a heart, and a diamond really doesn't look like a diamond. It's actually it's not a parallelogram. Well, sometimes they are. Depends on the deck of cards. This one it looks like. So it is a parallelogram, I suppose, but it's kind of a special parallelogram because I believe this might actually be a rhombus. It's not a star. All right. In each suit, you have an ace. And then you got a 2 and a 3 and a 4 and a 5 and a 6 and a 7 and an 8 and a 9 and a 10. Do we have an 11? No, it's a jack. Okay, and then a queen, and a king. So if we have 4 suits with, let's see, ace through 10 is 10, jack, queen, king is 3 more. We have 13 cards in each suit. So 13 times 4 is equal to 14, not 13. 13 times 4 is equal to 52 cards in the deck. So you have to know, you have to have this stuff memorized. You have to know how many suits there are, you have to know the colors, and you need to know that there are 52. Okay? It is a lot, but if you visualize it, and if you ever need to visualize, I always have cards that you can look at. Okay? I'm not going to have you sit there. Oh, look at her. Jerry's got her. I'm not going to have you sit there and like organize them all because that takes too long. But if you just needed like a visual, always have these keys. Okay, so we're going to need that for part C. So take a few moments and see what you can do with A, B, C, and D. Specifically C, we just talked about the standard deck of cards. So see what you can do with those 4. Come on now. Pause.
But how many are there?
We have established that we have 6 sides to a die. So that means my denominator is 6. So your total number of possibilities goes on the bottom. 2, 3, or 4 are 3 numbers. That goes on top. That's a half. Okay? All you got to do. Okay? Let's stick with fractions. So unless the problem initiates things with a percent or decimal, let's stick with fractions. HH, well, I have 4 possibilities and 2 heads is one of them, so that's 1/4. Standard deck of cards. How many cards are in the deck? 52. So that's my denominator. How many of the 2 suits? How many of the 4 suits, excuse me, are red? 2. So there's 2 red 6s. I got a 6 of hearts and a 6 of diamonds. So that's 1 out of 26. Questions? On a 6-sided die, how do I roll a 7? You don't. So this is just 0. And sometimes your probability will be 0. So if it's an impossibility, the answer is 0. Okay? So remember, it's a die, not dice. And we'll talk about a pair of dice. And we'll actually talk about craps and how it works and why it's not a good idea to play that game. Or pretty much any game where you're playing against the house. All right. Blackjack's a little safer, but
because they always have to be 16.
All right. What is the probability I will choose milk as my choice of drink? How many drinks do I have choices? I got 3: soda, water, or milk. So that's 1/3. Okay. Probability to choose a hot dog meal. Well, there's 3 types of food there, and that's 1/3 as well. Okay. Now, if I start getting more specific, what's the probability of picking a hot dog and then soda and then either dessert? Well, then that's going to be. Well, first, it depends on whether I'm being specified about the hot dog. So today we're keeping things super basic, not too distant future, like, I don't know, tomorrow or Monday, we're going to talk about conditional probability, where we're not looking at the entire sample space. But if we look at the entire sample space, you can see these are just the abbreviations, PSC. So that means a pizza with soda and cake. Or pizza with soda and ice cream. Pizza with water. Okay. Yeah, there's no salad in this one. This is not a healthy meal. I mean, except for the water. So, look at the bottom. Okay. I'm going to talk briefly about something called the counting principle. Counting principle is really simple. Okay. Here's what the counting principle says. Counting principle. Principle. Okay. Have multiple events. Okay. The total sample space is the product of the events. In this case, I have 3 events. I have 3 choices, 3 choices, and 2 choices. So in this case, for this example, I got 3 types of food. And then I got 3 types of drink. And then I got 2 types of dessert. I don't have to work out the whole tree diagram here to figure out how many total I have. 3 times 3 times 2 is 18. And I can confirm this if I look on the bottom. 1, 2, 3. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay. So that's my total number of possibilities. All right. Come on now. All right. When we talk the universal set, that is all of our possibilities. Intersection is we have just taking things 2 at a time. Can we take them more than 2 at a time? Oh yes, but not in this class, okay? We could take them as many possibilities. So if we have multiple events going, we have multiple intersections. We're going to keep this relatively simple though. 2, and I think in the next case maybe 3. So the union is including all of the events, okay, that are separate. And then the complement is going to be a little bit harder to describe until we actually get it. It's the set of all elements that are your universal set that are not in a particular set. So this will make sense in a minute when we do not this problem, but the next problem after it. So we're going to start with this one. Okay, we got 3 sets. We got red, green, and blue for our A. We've got red, yellow, and orange for B, and we have red, orange, yellow, green, blue, and purple for C. So we're trying to find the the union of the first 2. So if I'm finding the union of the first 2, that means everything that's in both of these, but we don't repeat something. What repeats in A and B? Red. So when we write the union, we only write the red once. We also have green and blue, which is in A, and we have yellow and orange, which are in B. Okay. So the union of those 2 sets is all of those elements. The intersection is the one that shows up in both. And the only one that shows up in both is the red. So since the red is in both of these, that would be the answer of my intersection.
I think the little squiggly on the outside.
The little squiggly on the outside.
Orange is red. Yeah.
Oh, the braces? Yeah. Okay, so when we write a set, this is using set notation is with the braces, okay? But it's on the keyboard. So if you do shift square brace, it'll make a pretty little brace, okay? So if I'm either in my equation editor or in my text box, come on now, don't prove me wrong. I can make curly braces really easily. You don't have to make them by hand. Okay? It took me years to perfect that. All right, let's look at the next one. So this would be a scenario of students in a senior class. Take a minute and read it. And then we are going to fill in this lovely, what's this called? Venn diagram, okay? With a Venn diagram, you have to keep something in mind. Whenever I put a number someplace, it's significant, not just the number, but the position. So where do you think, and I looked most around, most people starting in the right spot, where do you think we should start? Matthew?
The middle.
Okay. Most of the time, when they give you a bunch of sentences, you're probably going to start at the end. And this is not an exception. So we're going to work backwards. So we're going to start with the 62 and put that 62 in the middle because attending both would be the intersection. So I'm just going to set up my little equation editor and put a 62 right there. And now it's time to start thinking. First, I need to define these. Okay. So let's use GC for graduation ceremony. And GP for graduation party. So on the left and on the right, you have to define. If I give you a blank Venn diagram like I'm doing here, you got to define what each one is. So if I start with go backwards and start with the party, okay? So 143. Why can I not put a 143 right here? Because I already have how many? 62. So the entire circle has to be 143. So if I want to know people who just went to the party, it's 143 minus the 62 we already have. Okay. I think that's 81. So now what I want you to do is find the number of people that just went to the ceremony and then answer the questions for A and B. And there should be another number here, and we're going to talk about what that means too. Okay. So go ahead and fill in the rest, answer the questions, and then we'll kind of go from there. What do they mean? So first, let's find out the number of people who went to the ceremony but did not go to the party. So just like over here, we subtracted, we're going to do the same thing. But we're not using 143 this time because we only had 78 seniors. See how you're going back? We were at the 62, then the 143, now we're at the 98. Okay? Just be systematic about this, and it'll work out pretty well each time. So I got 36 students here. So it says find grad party. So this really means graduation ceremony union with a graduation party. That, I'm going to get fancy here, is all three of those numbers combined.
Yep.
Everything within both circles. That's what the union means. So here, I just add them up. I got 36 plus 62 plus 81. If you add them all up, you have 175. The part, 179, thank you. The part in the middle is literally
The middle.
this piece is the same as that. So that's just the 62. So that's the easy part. There's no adding or subtracting. You just use the union. We got 185 students in the senior class. Looks like
6 of them.
we have 6 of them. We don't know if they didn't graduate or they just didn't go to the ceremony. So this is what's known as your complement. Okay? So this would be the complement to the union. So our universal set includes everybody. So if it's not in one of the events, it goes outside in a Venn diagram of the circles, but still stays within that box. Okay? And then all of the numbers should add up to be my total, which is 185. Questions?
Nope.
All right. So these are your different scenarios. So I've it's got the 52 cards. So it shows every single event, which is just every single card in the deck. Sample space of rolling a die, 1 through 6. So it's just really specific. And here's the last one I wanted of marbles. Here's the last one to talk about. So the 36 outcomes in the sample space is actually your game of craps. Okay? This is how craps is played. And actually, that's the real legitimate name in a casino. They have this big, you've probably seen it in movies, this big felt table that is kind of dropped down. I know it has a specific name for it. And then a high side. So you lean over and you throw the dice. Okay? And what you're trying to do when you throw the dice the first time is get the lucky number. What's the lucky number? 7. Okay? And the reason it's lucky, it's pretty simple. Okay? Let's use a different color. 5, 6 plus 1, or 5 plus 2, or 4 plus 3, or 3 plus 4, or 2 plus 5. It shows up 6 out of my 36 times, which is more than any other number. When you roll a pair of dice, that's why 7 is lucky. Ahmad. Okay. So, but is it really that lucky? It's 1 out of 6 times. So if you roll a 7, when you first are the person who throws the dice, and you do it the first time, you win. That's great. You win. You roll a 7 again, you win again. But the chances of doing that is what? 1 out of 36. I roll it again, it's 1 out of 216 every time. So rolling a 7 is not so easy. So if you don't roll a 7, say you roll let's use a different number, different color. A 5. Okay? Before you roll that 7, you have to roll a 5 again. So let's see. Yeah, so there's only 4 ways to roll a 5. Okay. And then some people they have different bets when they do it. It's like, okay, I'm going to bet that you roll a 3 and a 2 again. Well, that's a 1 out of 36 chance. So your payout's going to be really good, but that's only going to happen 1 out of 36 times. Okay. So craps kind of sucks. It's great for the house. They make lots of money. Okay. And people get all excited when somebody wins. Oh my gosh, they rolled a 7 6 times in a row. They just made $25,000. Hey, I did it 7 times in a row. I can do it an 8th time, right? Okay. It's not good. Okay, so gambling, not smart. Okay, playing against the house, craps, roulette, not so smart. The only game that you can play against the house that you have a decent chance of odds is blackjack. Okay, because with blackjack, they actually lose about 40% about 40% of the time. Okay, they're still going to win more than half the time, which means they still make money. Unlike these, where they make money like all the time. All right, so these are different sample spaces. This is a very specific version of how we do it. 3 flips of a coin. So it explains explicitly why there are 8 sample space outcomes. If I have flip it a 4th time, what's it going to be? Not 8 anymore. Now it's 16. And then 32. And then 64. Have we seen these numbers before?
Yeah.
In your geometric sequences?
Oh, yeah.
That's what it is. Okay? So your denominator is just a geometric sequence of the power of 2. Okay. And I think that's about it. Oh, okay. Nope, we got one more. So this says, what's the sample space for flipping a coin and rolling a number cube? Hey, when you do the class assignment, this is it. Okay. This is one of them. I would make it vertically, not horizontally. So we have heads or tails, and then dice. I think in that case, it's actually, in the assignment, it's reversed. So you'd have the numbers 1 through 6, and then heads or tails. Okay, and that, I think, is about it, because the rest of this stuff is from a smart board. It doesn't work. So we are going to stop there.